Welcome to part 1 of Green's theorem. Green's theorem states the relationship between a line integral and a double integral over a simply connected plane region R. The double integral over the region is equal to the line integral around the region counterclockwise. So the region needs to be simply connected and piecewise smooth, and the orientation must be counterclockwise. So looking at this first region, R, notice the curve around the region is oriented counterclockwise and it's smooth. Looking at the second region here, the region is piecewise smooth, meaning each of the four pieces of the curve are smooth, and therefore, because the orientation is counterclockwise, we could also apply Green's theorem. And then it won't apply to us in this video, but you can extend Green's theorem where you have a simply connected region, as we see here, with a hole in it. But again, this won't be addressed in this video. So let's see what Green's theorem says. If C is a simply connected, piecewise smooth curve with a counterclockwise orientation in a plane region R, and our vector field with components f and g have continuous first partial derivatives, then the line integral, written here as f dotted with dr, or in differential form, is equal to the double integral over the region of the partial derivative of g with respect to x minus the partial derivative of f with respect to y dA. And since we just talked about the fundamental theorem of line integrals, notice that if this difference was 0, the vector field would be conservative. So the vector field does not have to be conservative to apply Green's theorem. When the path of integration satisfies Green's theorem, we can denote the line integral as we see here, which tells us we have a closed path line integral. So in short, if Green's theorem is satisfied, it often gives us an easier method to evaluate a line integral. And again, the vector field f does not need to be conservative to apply Green's theorem. So instead of parameterizing everything in terms of t as we did several sections ago, if the region is piecewise smooth connected, oriented counterclockwise, we can apply Green's theorem. Let's take a look at our first example. We want to evaluate this line integral where c is the circle x squared plus y squared equals 4 transverse counterclockwise. So our region satisfies the requirement of Green's theorem. So we're going to rewrite this line integral as a double integral over the region R. So the x component of vector field f is equal to little f, and the y component is equal to g. So the partial derivative of g with respect to x would be 1 minus the partial derivative of f with respect to y would be negative 1. So here we're just going to have the double integral over the region of 2 differential a. Well, this is just 2 times the area of this region. This would be 2 times, well, the area of a circle is pi r squared, and the radius here is 2, so we'd have pi times 2 squared. That's going to give us 8 pi. However, I do want to go ahead and show how we could evaluate this if we didn't recognize that this is just 2 times the area of the region. So to evaluate this over this circle, it would be much easier if we converted this to polar form. And remember, when we do that, we have an extra factor of r and then dr d theta. Well, r would be from 0 to 2, and theta would be from 0 to 2 pi. Again, we know the answer should be 8 pi. Let's go and just verify it using the longer method. And let's go ahead and evaluate this on the next page. So we'd have 2 times r squared over 2, which just gives us r squared. This would just be 4 minus 0, so we'd have the integral from 0 to 2 pi of 4 d theta. So we have 4 theta. And then you can see here we'd have 8 pi minus 0 or 8 pi. So the result is the same, regardless of whether we take the shortcut by just multiplying 2 times the area of the region, or we convert to polar form and evaluate it the long way. Let's go and take a look at another example. So we have the same type of problem. We want to evaluate the line integral where c is given below along y equals x squared over 2, that would be the curve, and y equals x, which is the line, and this is transverse counterclockwise. So the region does satisfy Green's theorem. So to evaluate this, let's go ahead and convert this to a double integral over the region R using Green's theorem. So again, little f would be the x component of the vector field f, and g would be the y component. So our line integral is going to be equal to the double integral over the region R of the partial derivative of g with respect to x, that's going to be 2x, minus the partial derivative of f with respect to y, that's going to be 2y, differential a. Now we need to decide the order of integration, meaning do we want differential a to be dy dx or dx dy? Since our equations are functions of x, I'm going to go and integrate with respect to y first and then x. So limits of integration for y must be expressed as functions of x. So the lower limit will come from the curve, that'll be x squared over 2. Upper limit for y would be the line, which is y equals x. And then for the limits of integration for x, it'll go from 0 to 2. So we'll first integrate with respect to y, that'll give us 2xy minus 2 times y squared over 2, or just minus y squared. We'll evaluate this at our limits of integration. Remember, we're replacing y with our limits of integration. So we're going to have 2x times x, that's 2x squared, minus x squared. And we'll have minus 2x times x squared over 2, that's going to give us x cubed, minus x squared over 2 to the second power is going to give us x to the fourth over 4. Combining our like terms, we'll have x squared minus x cubed plus x to the fourth over 4. Let's go ahead and finish this on the next page. So we'll have x to the third over 3 minus x to the fourth over 4 plus x to the fifth over 5 times 4, x to the fifth over 20. So when x is 2, we're going to have 8 thirds minus, this will be 4. Here we'll have 32 over 20. And then when x is 0, we'll have 0. This works out to 4/15. And we'll stop here for this video. In part 2, we'll take a look at some additional examples of Green's theorem. Thank you for watching.